You can start again. All right, so now let's talk about the other thing on your sheet, which is an orbital diagram, okay? Now, an orbital diagram, did you notice it was very kind of similar to the electron configuration?
Yep.
Except for, we had a few more things, okay? We had one box for the S, another box, one box for the 1S, one box for the 2S. How come I had 3 boxes for the 2P?
Because they come in pairs.
They come in pairs. Okay, very good. All right, here's the deal. S, P, D, and F are what we call sublevels or sub-energy levels. Okay? The 1, 2, 3, 4, the big numbers in front, Rob told us these were just the energy levels. Remember, we're graduating from calling them rings or shells. Those are actually energy levels. Okay? Now, so energy levels are broken down into sub-energy levels or sublevels. Okay? And then those, a lot of you talked about a pair. Inside energy levels are what we call orbitals. And you are absolutely right. Orbitals can only fit 2 electrons apiece. Okay? So 2 electrons fit. How about that? Okay, so it's a pair. All right? So if the p orbital can hold 6 total electrons, how many orbitals must be in there? 3. That's right. 1, 2, 3. Okay? If we have a d sublevel, how many orbitals will be in the d? 5. And F, how many will be in there?
7.
7, right. Okay, in fact, I want you to see something. So how many orbitals are in an S?
2.
1. Okay, so an S has 1 orbital. How about a P?
3.
3. How about a D?
5.
And how about an F?
7.
7. Okay? If we were to have another sublevel, let's say we discovered a super element, and we needed more energy levels, more sublevels, what would be the next sublevel?
9.
9, very good. And how many electrons would you predict could fit in there? 18. You see the pattern? 1, 3, 5, 7. And double that is where we're getting the 2, 6, 10, 14. Okay? So there's a lot of patterns, and they're not coincidences. Okay? If we get into a discussion of quantum numbers, you would see why these numbers worked. Okay, and we'll save that for another day. Okay, so here we have the 2p, and then the 3s just has one orbital in it. Okay, so when I'm filling this up, what am I going to put in here?
Arrows.
Arrows, and the arrows represent electrons. Do I put, this is 1s2, do I put them both up?
No.
No, why is that bad?
Because it's just not how it is.
Cause. All right, you guys know not to do it, but do we know why? Okay. Does it,
Going in different directions. So
Okay, they are going in different directions, but why do they have to go in different directions?
So they balance each other out.
Counterbalance.
Okay, who said something about charge? Ariana, what were you saying?
They're both negatively charged.
They are. I mean, when I think about a nucleus, I just get totally freaked out. There's all these protons smushed in this little space. I mean, how does that even happen, right? There's a whole bunch of explanation for that. But we're talking about electrons right now. If you have 2 electrons in a small space and both electrons are negatively charged, won't they repel? Yeah. And guys, do you think if things are repelling that we have low energy? No. So if we're trying to lower the energy of our system, I mean, and it's, again, it's not us that told the atom to do that. When we research and collect data from all these atoms, okay, we notice they're in the lowest energy possible. So when we're trying to figure out how it must look inside there, then we know that they're minimizing the energy. So you minimize electron repulsion in order to minimize that energy. So that's why they spin in opposite directions. Does that make sense? Okay. All right. So we have 2 electrons here. We have 2 electrons here. And you'll notice some people will just do this. They'll draw a half arrow. They're the same thing. They're just getting lazy, or they're just trying to go quick. Okay, it doesn't mean anything. Okay, now, this is what's interesting. The 2p, 6 electrons fit in there. Okay? The one thing I want you to understand is that all the energy in the 2p electrons, every orbital has the exact same amount of energy. In your book, sometimes they'll call them degenerate orbitals. I never learned that term when I was going through school. I discovered it when I was a teacher, reading in the book and seeing it in a problem, going, what is that? Oh, yeah, that's that equal energy thing. So I just wanted to kind of expose you to that term. We don't use it a lot. But if these all have the same energy, is there any reason to fill one before the other?
No.
No. And so if we're trying to remember, there's all these different kinds of energies that you have to think about. Okay? So what would be the best way to fill this up? Michelle?
You start with like each one in each box and then go back.
Very good. So if we're putting in 6, we would put 1, and then 2, and then 3. We're getting them far apart, so we're minimizing electron repulsion. But now if we have to fit in 3 more, then they're going to go here, here, and here. Does that make sense? Okay, now let me ask you this one question. If it causes energy, if there's a little bit of repulsion by putting 2 in 1, why don't I just go up to the 3s?
Because you're not on that energy level.
Well, I'm not on that energy level, that's true, but why don't I just go there?
Because you can't.
Well, here's the deal. It must take more energy to go up to a 3s than to pair them up in opposite direction. You see what I'm saying? Everything is about getting to lower energy. So if we observe that the electrons fill up the whole 2p before it goes to the 3s, then this must take less energy than going up to the third energy level. You see how it's all a description of energy, okay? All right, so we have our 2, okay, and then we have just 1 electron, and it doesn't matter whether you put it up or down. It really doesn't matter, just as long as once you get 2 in there, they're opposite, okay? All right, then we had, what was on the sheet? It asked you for the ion, is that right? Or no, the Lewis dot structure?
Mm-hmm.
Okay, so the Lewis dot structure, what do we care about? So how many electrons in the valence?
1.
1. How did you know that? How many of you are looking at the chart and seeing that it's in the very first column? How many are doing that? Okay, good. That's great. So you know it's 1 valence electron. Okay, go back here. Look at your electron configuration. Remember, the front numbers tell you the energy level. Which one's the biggest number?
3.
The 3. So these are the valence electrons. Okay? And there's just 1. So you would just put 1 dot. Okay? If it had been 3s2, 3p5, okay, then the 3s and the 3p would all be the valence shell. Okay? And you'd have 2 and 5, you'd have 7 valence electrons. Make sense? Okay, so this is the Lewis dot structure. Then I ask you for
Ion.
the ion formed. Okay, what would sodium like to do? +1. You guys have known that from Chem 1. You can look at the periodic table and see that it's in the 1A, right? It's +1. But also here, you can see it's a metal. It's going to lose that electron, right? Okay. And tell me this about energy. Why would this be more stable than this?
Because it's bonded.
Full shell.
If I don't have this, have I had to input enough energy to go up to the 3s?
No.
No. You see how it's less energy?
Yes.
Okay, very good. And then the name of this was just the sodium ion.